Okay, good morning everyone. So it's already 2 minutes has passed. Let's start where we left yesterday. And before starting, if you have any question, if you try to read up, if you have any question, then you can let me know. Otherwise, on the way, you can also like tell me, right? So what we were talking about yesterday, that just a minute. So let me zoom it a little bit so that you can see. Okay, good enough. So what we had yesterday that so if I have my system and I define a macro state of the system. So to define the macro state, basically, I need to define how many number of particles are there and how much total energy is available to the system and how much volume a system is occupying. So if I specify these three parameters, then I would say that I have defined the macro state of the system, right? System is any physical system, it can be, it doesn't matter. Right now we are not interested in what type of particles these are. So n is the number of particles, it doesn't matter what type of particles they are actually. So but we are just interested in their statistic basically, right? So just give me a minute. Just give me 1 minute. Just a minute. Okay, can somebody comment and tell me if this screen is visible? I think it should be visible, right? There should be no problem. Okay, so yeah, okay, Kanksha, thank you, I got it. Uh, so now this is what I said yesterday, and I also discussed last time that they must satisfy certain constraints that these type of thing that my Ni, Eis, this must be the total energy summed over I's, right? And why this is happening? Because I told you that if I have a discrete level of systems, so this is level 1, level 2, level 3, level 4, and so on. It doesn't matter how many number these are. Okay, so then if n1 number of particles are occupying level 1, having energy E1, so this will be the total energy being contributed E1 to this total energy, right? Similarly, if there are n2 number of particles, and because it is energy level 2, so this is basically I index. Okay, so running over here, if we want to write here from 1 to suppose some n, then this will run up to n. So it's easy to see, right? So similarly, energy contribution of second level, it would be energy of this level times the number of particles occupying this level. So this will be the contribution towards this. So if I sum over all those energies, so then I will get the total energy. This constraint has to be satisfied by this macro state. So whatever macro state is accessible. So then similarly, I also must satisfy this condition, the total number of particles which are occupying all these levels, so they must sum to total number of particles, right? So this I would say n appears here, and volume, as I said yesterday also, and you will see this in examples that this basically comes via energy. So energy expression, the discrete energy being continuous energy, be it continuous energy, be it the discrete energy. So this volume or the space or dimension of the space occupied by the systems enter via energy expression, right? So if you define n's and e's and v, then I can have in principle say that I have defined the macro state of my system. Okay. Now, yesterday I also discussed this thing that there are different possibilities or different ways to satisfy these constraints, and each of such possibility is termed as microstate, microstates of my system. Okay. And we symbolized this number by omega. So number of micro, this is just a symbol for omega, sample for a number of microstate. Okay, this omega, don't get confused with anything else. So but it depends upon what is the macrostate. That's why we write the functionality of this number depending upon the description of my macrostate. So this was what we have done yesterday, right? So then I introduced this thing that we are going to talk a bit about how the statistics or this consideration, this whole consideration or distribution of particles kind of thing, or defining microstate for a given macrostate is going to generate the thermodynamics of the system. Okay, so that's what we are going to see today with some examples, and we'll try to see how far we can go. Okay, so just to put the ideas forward, I am going to consider two different systems, a1 and a2. Let me take a different color because both looks blue, so let me take red. Okay, so I'm having system A1 and A2. They are different systems. Here they are joined, but actually they are different. So respective number of particles, the volume they occupy, and total energy they possess are symbolized by this. So this is the basically the macro state of system A1. Similarly, this is the macro state of system A2 being represented by N2, V2, and E2. Okay, so the number of microstates accessible to this macro state N1, V1, E1 is being represented by omega 1, right? I think it should not be a problem. We are just extending the ideas which we have developed last time. So similarly for system A2, my number of microstates accessible for this macrostate N2, V2, E2 is being represented by omega 2. So these are number of different possibilities which a system can be in at a given time. Okay, so now the idea is, or this is I would say proposal, that the thermodynamics of this whole system can be we can drive it if we know what is omega 1 and omega 2. This is just a proposal, and you will see how this is going to happen. Okay, let me see. Okay, so now the idea is that this system A1, A2, they are isolated from the environment. So there is nothing is going to enter or leave this system, be it energy. We can't expand its volume. We can't change the number of particles in this system. Everything, like it's in full isolation from its surrounding. Okay, similar conditions are for A2 also. But now what we do is this wall, we make it a thermally conductible wall. So they are, I would say, so A1 and A2 are in thermal conduct, are thermally connected. So thermally connected, which mean to say is they can basically exchange energy. So this E1 and E2, that can change. Volume can't change because this wall is not movable. That's not I'm allowing as of now. And also the number of particles of system A1 and number of particles of system A2, they are also not going to change because this wall is not a penetrable one. Okay, later we'll see we can allow those, we can relax these conditions also to generate further thermodynamics. But for now, we are just permitting energy to be exchanged between the system A1 and A2. Only E can exchange, right? So what is going to happen? So this is what I said. So we will bring them into thermal contact, right? And this, as I already said, that these N1 guy, N2 guy, V1, V2, they all remain constant independently. Okay. Now, as I said, that whole this whole composite system is what? this composite system, right? Which is sum of A1 and A2, and it is being represented by A0. So as a superscript 0, it means it's a composite system of A1 and A2. So the total energy of this system before they brought into the thermal contact was this. Although I allowed energy to be exchanged between these two systems, so the sum of these two energies can't be a variable thing. And here I am again, as I said last time, I am not allowing any interaction energy. So there is no interaction energy for simplicity. Okay, so there are no interaction energies. So although E1 can change, E2 can change, but the sum is not going to change. So this is going to be a constant. Okay, so these are the condition for this system. Now you know if their energies are initially different, so they want to attain certain equilibrium. We are basically interested in driving the condition on these omega 1s and omega 2s. This is basically statistics. You must have this picture in your mind that what part we are driving from statistics and how this is going to lead to the thermodynamics of the system. Okay, so this distinction must be clear at every moment. Only then you can appreciate the beauty, otherwise things will get confusing. But you can ask any question on the way also. Okay, so yeah, as I already said, there is no interaction energy between the systems. So this we already said that omega 1 is representing the number of microstates accessible to system A1. Similarly, omega 2 are the number of microstates accessible to A2, and here it is only written as, if you observe, as a function of E1 and E2 only, because my all other four parameters N1, N2, V1, V2, they are constant, right? So if a function varies, we only are interested in a parameter which is a variable, right? Because omega 1 is going to vary only if E1 is going to vary. Okay, so the macro state of system A1 is going to change. For example, if you remember, initially the macro state was like this: N1, V1, just a minute, N1, V1, E1. So this was the macro state of my system A1 before we brought these two systems into thermal contact. But now these are fixed, so we are not more, any more interested in this. But this guy is going to vary because we are allowing energy to be exchanged due to this thermal contact, right? So we are only writing a number of microstates accessible. Obviously, this omega 1 is also going to change, right? Because E1 is changing. So omega 1 is changing because of this E1. That's why we only wrote this functionality like this. Similar argument is for omega 2 is also there. Now, if we are interested in writing the total number of microstates accessible to this composite system, it will be just a product of these two guys. Okay, let me see. Somebody message something. Sir, how can the volumes be constant independently? Tariq. Okay, Tariq, it is something like, suppose you have two rooms in your home, right? Like all the walls are like insulator, thermally insulated, and they are not movable kind of thing. Then you just uh, insert a sheet or kind of make a door which is made up of metal, for example, between those two rooms, right? So the energy from one room can flow into another. Okay, actually I don't want to say this right now because I want to see this coming naturally from the statistic. Actually temperature is going to equilibrate. Suppose if one room is cold, other room is hot, if there is a, suppose, a metal wall in between, right? You know that ultimately both room are going to have same temperature, they will be in thermal equilibrium, right? But because all the walls are fixed, so volume is fixed, so they can independently constant, right? So I think there should be not Gitika is saying how E naught is constant. Gitika, because E naught is the sum of energies of the two systems. Okay, so both these systems have their energy. It's something like, for example, I have 20 rupees in my pocket and you have suppose 10 rupees in your pocket. We can exchange that money, but sum will always remain 30. Yes, I'm not taking money or giving money to some third party. You are also not taking or giving money to from some other guy. Okay, so then our total will remain constant, although my money and your money can change, right? So total will remain constant. Okay, good. So if you got that, then nice. Yeah, I'm happy that you are asking, and next time I will unmute. Okay, let me see. Are we considering A1 and A2 as new single systems? So Bhagya, it's not new single systems. They are like independent system originally. Then we brought them into thermal contact. Okay, they have their own macro states defined by N1, V1, E1, and N2, V2, E2. But when we brought them into thermal contact, only energy, we allowed energy to exchange. So volumes were constant, number of particles were not allowed to exchange between those two systems, right? So they are not new, they are two systems. That's it. Okay, good. So now hope you must understand this relation that how I'm writing. I'm just writing the total number of microstates available for composite system. This A0 guy, right? It will be just product of the microstates available to this system, right? So it's like a probability multiplication kind of thing. So suppose you have two different possibility to be in two different state. I have the possibility in three different state. So jointly we have six different possibilities to be in six different state. Because I can be in my first state, you can be in first and second. I can be in my second state, you can be in first and second. I can be in my third state, you can be in your first and second. So this makes total number of permutations as six. So 3 into 2. So similarly, if you look for the total number of microstates available to the composite system, so this is just the product of the individual number of microstates available to the individual systems. And this functionality, there is a trick in changing the functionality here. So if you see from here to here, we just replace E2 by E0 minus E1, right? Because E0 was E1 plus E2. So that functionality we have changed. And by the way, E0 is constant. So basically this is this whole thing. If you see, the total functionality is only the E1 and E0. Nothing else. E2 is not appearing. Actually saying one and same thing. So this can be said that the number of microstate accessible to the composite system is a function of the total energy as well as energy of system 1. This can equally be written like omega of composite system. Actually I have to put a 0 here also, right? So equals as a function of total energy of the composite system comma E2. You can build holes this statistic by writing like this also. Okay, so this is equation number 2. If you see now, let's move ahead little bit, see that what argument I'm going to give you for the equilibrium. Okay, so let me see what question somebody raised. Yeah, Tariq is saying since E naught is constant, can't we write omega just as a function of either E1? Yeah, that's what we wrote, right? So that's what I just said, Tariq. So we just wrote no. Okay, you are saying just as a function of E1 or E2. No, because E naught is a constant, but E naught has certain value. So if you change the E naught, then E1 and E2 also going to change, right? Sum of E naught, E1 and E2 is constant, but that constant we can change. Okay, so we can begin with initial different energies. Then your number of microstate accessible to the composite system is going to change if I change the initial energy, right? So it means that total energy E0 has to come into the functionality. Okay, so now the question is that if this guy, the number of microstate accessible to the composite system, it varies with E1, or if you are interested in, you can write the expression other way. It also varies with E2, saying same thing in from another perspective. So my question would be that at what value of E1 my system, composite system, will be in equilibrium? This is the question now, because we allowed their thermal contact, so they will attain some equilibrium state, but we are not as of now aware of that what that equilibrium state will be, right? So here one assertion is there that the system is going to equilibrate in that configuration or that value of E1 for which this function omega is going to get maximized, right? So it's something like the most number of microstates available to the system is going to spend maximum time in that particular you can say macro state, right? So because you can have varied number of e values, so e1 can have some value e1 dash, so it can have another value e2 dash, so then it can have another value E3 dash, right? So this 2 is like, okay, so, and so on. So it can have I should not use actually E1, 2, 3, 4. Let me correct it again. So it's, I would say E1, because it's the value of E1 only. E1 double dash. So then another value it takes, suppose E triple dash, in such a way that every time by this omega of composite system, the number of microstate accessible to the composite system, now we just notice that it is depending upon just total energy and E1. Just E1. You can build the arguments, a similar argument considering E2 here also. So as this E1 is going to take different values, which is basically the different values of the energies while being exchanged between system 1 and 2. So this E1 is going to change, although this is going to be constant. So the number of microstate accessible to the composite system, this is also going to change. The idea is, or this assertion is saying, that that value of E1 is going to survive or attain equilibrium, for which this number is maximum, right? So then if most number of the I would say microstates are available, system is going to spend its time in that particular macrostate. Okay, so that's the idea. And this you can say principle is going to help us. And let's say that the value of energy at which this guy attains its maxima is E1 bar. So this is the energy constant. So at this value, so we attain the equilibrium. At that particular value, E0 is E1, sorry, E1, the energy of system A1 as E1 bar. So this is the equilibrium value, right? And E2 is equal, and this would also be equals to energy of the composite system minus E1 bar, because E1 bar and E2 bar will again be, are going to be equals to total energy, because total energy is not going to change. Okay, so now if we are interested in maximizing, now let's see, building upon these physical arguments, so what we can derive out of this. So we are basically saying that differential of this guy omega 0 must be equal to 0, because if it is maxima or minima, its first order derivative is going to be 0, right? You can do this with E2 also, same result will come out. Okay, so now we had expression for omega, which is omega 1 E1, omega 2 E2, and this EQ means we are talking about equilibrium condition. This is going to happen, or this is going to get equal to 0 only at equilibrium. Okay, so if it doesn't, it haven't attained the equilibrium, then this is no not 0, because then this number of microstate is not maximized yet. Okay, so now okay, let me write this. Actually, this is not a very complicated thing to write. So what I'm saying is, let me see if I can, yeah, so what I said is that at equilibrium, I usually make notes, because writing over stylus is not that good. So that's why I prefer notes, writing on notes. Okay, that's okay. So I was just saying that d by dE1 of this guy omega of composite system at equilibrium, this is going to be 0. Okay, so if that's the situation, and we just wrote that my number of microstates for composite system, it is nothing but omega 1 as a function of E1 times omega 2 as a function of E2. So if I feed this value here, so then I would say, so you are nothing required, you just need to apply u into v type of formula. So it will be first function as such, derivative of second function, so that's d omega 2 as a function of E2. Now do remember that you can't differentiate it with E2, right? Sorry, E1. So you have to differentiate. Actually, we should use the partial derivatives. This curly omega 2 as a function of E2 by curly E2. In fact, here we can go for full differentials also. So then your d E2 by dE1 plus curly omega 1 E1 by curly E1. This quantity must be equal to 0, and at what values? At E2 is equal to E2 average, not average, the equilibrium energy value of system 2, and this is going to be derived or differentiated at E1 is equal to E1 equilibrium value. So this is going to happen, and I think you must understand or guess that this quantity is equal to -1. Why? Because E1 plus E2 was a constant, right? So if you do a DE1 plus DE2, so this is going to be a 0. So from here you can immediately see the DE2 by DE1 is going to be a -1. It basically says as much energy you take from system 1, it will go to system 2. So the change in energy of the system 2 with respect to 1 exactly -1, right? That's so easy to like understand. So this is what being written here. So I'll just show you quickly. It is written neatly. So this is what I said, and let's see what we can write for this particular result. So what we had above over here, if you see here, so here it is curly omega 1. Let's forget about this E1 for time being, by curly E1, and then being multiplied by omega 2, and then there is this term which is -1. So we can take this whole term on other side, and this minus will make it plus on other side. So actually then we take this omega 2 with this differential and this omega 1 with this differential, right? So then we will have term something like this. It will look something like this. Let me write it. So we have 1 by omega 1 curly omega 1 by curly E1 at E is equals to equilibrium value. On other side, I will have 1 upon omega 2 curly omega 2 by curly E2 at equilibrium value, right? So basically, if you see, so this is something which need to be same for both the systems. So you see there is only change of index, 1 1 1 1 everywhere. Here it is 2 2 2. So basically I will term this quantity as some beta function. Let it be beta 1, and this is equals to beta 2. So basically idea is that two system will be in equilibrium if beta 1 of the system 1 index means it is of system A1, right, becomes equal to beta 2 of system A2. Again this index 2 is means that it is of a system 2. So basically we have defined one quantity which I will take directly from this slide. We defined something like this, a beta parameter, right, which is just rate of change of log. Okay, I made a mistake, so which I should correct. uh Here actually this you can write as curly by, this is important actually, E1 log of omega 1. You can see when you will do this, so when you are going to differentiate this quantity with respect to E1 log, so immediate derivative will come out to 1 upon omega 1, because derivative of log x is 1 by x. Then curly of that omega 1 with respect to the parameter you were differentiating with. So this is a compact way of writing same thing. Okay, so beta actually defined like this also, both are equally good, right? But this is a compact way to writing same thing, nothing else. So because here I'm using the later part. So this is the beta of my system. So equilibrium means that betas of two systems have same value, then I would say that my system is in equilibrium. So what does this beta means actually, right? So if you have some memory, and if you recall from your thermodynamics knowledge from your bachelor's or BSc maybe second year, then you differentiate entropy with energy at constant number of particles and volume, then it becomes it's basically inverse of the temperature. Okay, so this is a pure result from thermodynamics. And if I just write this equation number 3 in very simple, I would say, notation, so this will look something like this. So this is a delta log omega by delta E. And see here, number of particles and volume is constant. Same is here, number of particle and volume is constant. This equation you can also satisfy rewrite as delta S by delta E kind of thing, which is 1 by temperature. Saubhagya, you are saying something, but that yet had to come. Boltzmann entropy relation. Okay, so that's good. But you know the answer. That's good. But I am more interested if you can appreciate the process. That how simple idea of number of microstates accessible to the system. We brought them into thermal contact. Automatically, we get so strong relation between statistical mechanics or statistics and thermodynamics of the system. So that's the beauty actually, right? So if you can appreciate that, then we are almost through this course, I would say. Okay, so every time you must understand first and then try to appreciate that what is happening. Okay, so so if you just use these two relations, right, and eliminate delta E out of it, you would see that I can very easily write that my delta S by delta log of this omega, where omega is my number of microstates accessible at equilibrium. So this would be some 1 by beta T, right? And this condition is true for every system. Okay, it doesn't matter which system under consideration, and same is the situation with this relation. This relation, we never gone into detail of the system, that what kinds of system we are dealing with. So we are just saying it's under equilibrium, these two are going to attain similar values. But to discuss this, that beta is defined like this, we even don't require the what you say equilibrium. So this is the definition of this beta parameter. So in this definition we don't require any equilibrium, mind it. Okay, so it means that this quantity or this ratio has to be constant independent of the system, because it's true for all the system. So this constant was should be, it was proposal by Boltzmann, as Saubhagya pointed out. So this constant was Boltzmann constant, right? K I would be representing it by. So, and this relation, if you just see, try to integrate this relation, actually this would be something like curly S by curly log of omega equals to 1 by beta t kind of thing. Okay, and this we named as or termed as Boltzmann constant, or it's a universal constant kind of thing. So if you try to integrate this, actually there can be some additive constant. Okay, but this has to be taken as 0, because why it is 0 I'll tell you very quickly. Okay, so if you take your omega is equals to 1, this guy, right? So omega 1 means you are in such a state then that for a given macro state your system has only one possible configuration of microstate. So there is only one microstate which is accessible to the system. So then at that case your system has no probability or no uncertainty. Okay, so it's a fully deterministic system, and in that case your entropy is going to be 0, right? So this is kind of you would say obvious from this relation, that log 1 is going to be 0. So this additive constant is going to be a 0 thing. So this relation is very central in whole of this, I would say, course, which relates entropy of the system with the statistics of the system. Statistic is here, the omega, the number of microstates, different configurations. So that's means laying here. And once we know what is the omega, we can derive the entropy. It's very straightforward. Okay, so okay, now I will quickly go, and this is nothing but I wrote directly, so that your beta parameter is 1 by kt. You might have seen this many a time, right? So beta parameter is 1 by kt thing. So it means saying that two system has same betas. So beta 1 was equal to beta 2. This means I was basically saying indirectly that T1 was equal to T2. Okay, so because in that derivation, when we are looking for equilibrium, so statistics ask this, if you see. So statistics asked this thing, this condition, that beta 2 become equal to beta 1. But if I try to link the related thermodynamics, then it says temperature should be same. And now you know that if two compartment or two boxes or two rooms or two containers, they are in thermal equilibrium, they in thermal equilibrium means they will have same temperature, right? So that's very obvious to understand. Now let's move a bit ahead. Okay, Tariq is like, can't we start this derivation by differentiating? Yes, Tariq, you are correct. This I think I said, but you pointed out nicely that we can derive this whole thing instead of doing with E1, we can do the same thing with E2 also. Both will give same result. But there is no fun if I do both of them. I did one, you can try other. That nothing is going to change. Okay, only thing which is going to change is this one. That this equation instead of mm, 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 yeah, so here now if you will differentiate this omega like this with E2, so you will have here E2, fine, then this term would come here. Then here you will have, okay, let me change color. Just a minute. Didn't change. I don't, okay, looks change. Good. So I'm saying that, let me see. Okay, it's running. So this will remain same, but this term won't appear because you are differentiating now this with respect to E2, because you thought to write these things as a function of differentiating this whole thing with respect to E2. So this won't appear. Then you will have this, but this will appear here as curly E1 by curly E2. And again this term will be -1, and after this everything will remain same, so it won't make much difference. But yes, you said it rightly, both like approach will give same result. Actually they should give same result, right? Otherwise there is no. Okay, since we equate it with 0, there won't be any change. Yes, Tariq? Yeah, I think I answered your query. Okay, so now, okay, so time is almost up. I think I should continue from this point next time, right? So I just want to, okay, I'll introduce what I'm going to do next. Then in next lecture we'll do that. So what my idea is that now in this discussion, I just allowed that energy can be exchanged between system 1 and system 2. Now I will make my wall such that it can move also, right? It's a movable wall, and also making A and A2 to exchange their energies, right? So basically now I am allowing E1 and E2 to vary, but their sum will remain constant. And also I am allowing V1 and V2 also to change. So my volumes are also going to change. So what type of equilibrium you are expecting? And I think you can very easily guess if wall is movable, but initially suppose system A1 and A2, they had certain different pressure, right? But to equilibrate, their pressure has to be same, right? So then we should get some parameter from statistic perspective which is related to pressure. So that we will see next time. And lastly, just to complete the discussion, I will also allow particle to exchange. Okay, so then I will have another parameter which need to be same for both the subsystems, similar to beta. So that will be actually chemical potential. That's gives free energy per particle. That's the chemical potential that need to be same. Then I would say my systems are in equilibrium. So once we have all these kind of equilibrium conditions under three different scenarios, then we can drive whole of the thermodynamics of the system. So that I will, I think, complete next time, right? Okay, thank you everyone. So that's enough for today. You can leave now. Thanks.